Metallurgy has advanced society for millennia. In addition to traditional roles, today, metals are essential to worldwide clean energy demands. That's because many of the proposed clean energy solutions hinge upon our ability to understand and predict how metallic structural components behave over time when subjected to extreme and complex environments, such as harsh temperatures or irradiation. The challenge is to anticipate how a metal will respond over its extensive lifetime.
As a metal is subjected to mechanical and thermal loads, or stresses, we must ensure subsequent deformation won't result in unfavorable or even catastrophic conditions. By predicting a material's response through theoretical deduction, rather than solely relying on direct observation, we can help mitigate problems and accelerate technology deployment.
Everything around us has internal microstructures, visible only with a microscope. Engineered structures, from bridges to nuclear reactors, inevitably have small changes in fabrication parameters that can result in unseen changes in microstructure. Individual components might look identical, but risk varies once you take the microstructure into consideration, and that risk might not be realized until many years later. Given the pressing needs for rapid technology deployment, tools are needed that give designers, regulators, and the public confidence in clean energy technologies. Fortunately, advanced mechanistic and microstructure-sensitive models provide a pathway to simulate the expected performance of a structural metallic component.
Los Alamos Reduced Order Model for Advanced Nonlinear Equations, or LaRomance, was developed to relate these microstructure scale states to the performance of large-scale structure, thus offering much-needed peace of mind. The suite of data-driven models predict the mechanical response of structural engineering metals subjected to extreme environments, such as those in nuclear power plants or turbines. These models fully integrate into finite element solvers to help us simulate the response of engineering structures down to the microstructure of the base metal. Usually, a series of laboratory tests are performed to establish the expected lifetime of a material system.
However, the testing can take more than a decade, and the actual conditions experienced by a material in use might differ from those in the laboratory tests. An ideal model should be able to extrapolate beyond the data available. LaRomance models draw from a database of advanced simulations that are sensitive to the microstructure of metals.
Our models can be applied to any arbitrary quasi-static loading condition, such as stress relaxation, creep, tensile test, and cyclic tests. LaRomance captures the entire spectrum of behaviors of the metal in a unified fashion. This development really opens new avenues to incorporate microstructural information into real-world decision-making.
For example, the ability to predict a material's response well into the future provides a solid pathway to accelerate deployment of nuclear reactor components, which must perform flawlessly while subjected to truly extreme conditions.
LaRomance introduces highly predictive tools as a turnkey solution to any user, regardless of their expertise in material science, all while reducing cost, increasing safety, and expediting deployment.